Okay, so hi everyone. Welcome to today's session. So last week we covered the basic, the subsystem code, the motivation that we start from the 9-qubit Shor code to get the Bacon Shor code. So this week we're going to still going on this session on the subsystem code by Derek. So let me hand it over to Derek now. Okay, thank you, Derek.
Hi. Yes, so today I'll be talking about the subsystem codes, and it's going to be, um, uh, I guess, an extension from last week's talk. So let's, uh, so I'm going to begin with a recap of the previous tutorial, followed by what the new Laflamme conditions are for subsystem codes, and then I'll give more examples and I'll explain why we are interested in subsystem codes, and finally I'll give a summary of what we discussed today. So last week we talked about the 9-qubit Shor code, and so this 9-qubit Shor code has high weight X stabilizer, so they were of weight 6, which is not ideal, and we showed that the Bacon Shor code with two body gauge checks, so with X with nearest neighbors X checks and Z checks, those are stabilizers. Those have stabilizers which are the products of these 2-qubit checks. And so these checks are a lot lower weight than the 9-qubit Shor code. And finally, we discussed what the subsystem code formalism is. So we talked about the logical and gauge subsystems, and we talked about stabilizer groups and gauge groups. But don't worry if that is not, if you don't remember what that is, because we'll do a quick recap. So a subsystem code with parameters n, k, g, and d is basically a decomposition of the Hilbert space, which is the 2 to the n dimensional complex space, into this A tensor B, which is typically what we call Q, and with the direct sum of this thing with Q perp. So Q perp is kind of like the space that we are not interested in. A tensor B, so this tensor product is over C if anyone is interested, but this tensor product would be the code space, and the code space is decomposed into a logical subsystem A and a gauge subsystem B. So the dimensions are 2 to the k for the logical subsystem and 2 to the g for the gauge subsystem. And what is slightly more useful is to define these subsystem codes in terms of the subgroups of the poly group, which could, so there are two of these subgroups. So one of them is a stabilizer group, just like the stabilizer code. It is a subgroup of Pn not containing minus the identity, and it fixes all the elements in A tensor B. So it fixes all the elements in the code space. And then we have a larger gauge group, which doesn't need to fix all elements in the code space, but rather it just needs to fix everything in A. So it fixes everything in the logical subsystem, but it could change something in the gauge subsystem. And the logical operators are the elements in the centralizer of S. So last week I said this was the normalizer. It's the same thing for the stabilizer group, but it is different for the gauge group. So last week I said this was the normalizer of G. That's not precise. That's not exactly correct. It should be the centralizer of G. Because the normalizer of G, if you compute it, it's actually just the entire poly group because it contains minus the identity. So yeah, the bare logical operators are basically those that commute with the entire gauge group, so things in the centralizer of the gauge group. And these would only act on the logical qubits, so it wouldn't act on the gauge qubits. And the dressed logicals are the ones that commute with just the stabilizers. Well, they could commute with the gauge group as well, but we just need them to commute with stabilizers. So there are elements in the centralizer of S, which is the normalizer of S, and these would this could possibly act on the gauge qubits as well. Right. So next we will now talk about the Knill-Laflamme conditions for subspace codes. So for subspace codes, this was covered in tutorial 3. We have Q, a quantum code. So this is a subspace or semi-Hilbert space. And P, we let this be the projector onto Q. So it means that we're splitting this space into a Q and Q perped. Q perped is the orthogonal complement of Q, and P is basically projecting the code onto Q. And it's basically zeroing out the orthogonal complement. And so when are we able to correct a set of errors? The Knill-Laflamme condition says that we could correct the set of errors if and only if, for any two errors in this set, we could find a constant such that this equation holds. So effectively, what does this equation say? It says that if we have an orthonormal basis of Q, so we take Q and then we choose an orthonormal basis. This equation is basically the same thing as saying that, I mean, you could multiply this by, the cat of the bra of phi of R, and then this, and then a psi of R, and then this, and then you'll see that it is basically a constant times the Kronecker delta of R and S. So if these two are the same, then it is a constant independent of what the two states are. If it's not the same, then it's zero. Yeah, it could depend on J and K, but it should not depend on R and S, this parameter alpha. Any questions? So this was covered in tutorial 3. So to kind of give a quick proof idea of how the proof of this went, if you want more information is in this Nelson and Trong. You could find a complete proof there, but as a quick overview of what the proof is, for a set of recovery operators, so assuming that the code is correctable, so we would have some recovery operators, and we could show that this taking anything from this set of recovery operators multiplied by any one of these errors in E, it must act as a scalar on the code space, which means that this product, which means that when you project on the code space and then you multiply it by this product, it should just be a scalar. And then you could add, and then you could take this, multiply by its conjugate transpose, and then sum this up across all the recovery operators, and then you would see that this equation basically falls out. And to prove the converse, which means in order to prove that this equation would imply that the errors are correctable, we first note that the matrix alpha jk, so alpha jk is a constant. If you collate all entries into a matrix, we could prove that this is Hermitian. It follows from the definition of what a Hermitian matrix is and this equation. And we could diagonalize this matrix, and then we get another set of errors which are equivalent. And this would satisfy this equation. So instead of alpha jk, now we get djk, but the difference is that now this djk is diagonal, which makes things very easy. Effectively, it's saying that if you have two different errors, well, if you have two errors, if you start off with two states and you apply two of the errors to the code, to each of these two states, the resulting states are going to be orthogonal to each other unless both the errors and both the states that you started off with are the same. Well, in this way, it becomes really easy to kind of distinguish what the errors are. Okay, any questions?
I mean, Derek, I think there are some questions. Sometimes people ask in chat.
Oh, okay.
So I mean, people can ask directly also because Derek is stopping to, like answer.
Oh yeah, feel free to stop anytime. Can A and B change? Yeah, A and B are not really fixed. I mean, there is some flexibility of choosing A and B. I mean, yeah, effectively, yes. You could change A and B. It's kind of like, I mean, A and B are not subspaces. They're kind of effectively what you're doing. You could think of so Q is your code space, and I mean, I like to think of A and B as just I mean, A is a subspace. I mean, A is an abstract subspace. B is an abstract subspace. And I like to think of, I mean, the tensor product of A and B having an isomorphism with Q. I mean, you could find like a linear map that kind of makes the two spaces isomorphic. So, yeah, I mean, it's not like A is not like a subspace of the space itself. It's not a subspace of Q. So, yeah. So there is choice. Any other questions? Okay, so now what are the new Laflamme conditions for subsystem codes? It is almost the same thing. Well, so we have Q, which is A tensor B. So previously it was just Q, and now we have A tensor B. So A is the logical subsystem, B is the gate subsystem, and again, P is the projector onto Q. Now Q is able to correct the errors in E if and only if for any pair of errors in E, there is an operator on B such that this a product which also appears in the new Laflamme conditions for subspace codes. Now this just has to be equal to the identity tensor product with some operator on B. So it basically you're allowed some freedom on this gauge subsystem B. And when we I guess when B is one-dimensional, then Q becomes a subspace code, right? Because when the gauge system is one-dimensional, there is effectively no gauges because it's 1 is 2 to the 0. And you see that this B becomes a one-dimensional subspace, so this GJK becomes a constant. It has to be some constant, so this basically reduces to the new Laflamme conditions for subspace codes. And an exercise for anyone interested is to try to prove this theorem using inspiration from the proof for subspace codes. Yeah, so I think this is best left as an exercise, but then people who are more mathematically minded would recall that a mathematician, Hendrik Lenstra, once said that a math lecture without a proof is the same as it's just like a movie without a love scene. So it is essential. So I will attempt to give a proof of the answer to the question of which sets of errors are correctable. So a set of errors, so this is the new Laflamme condition. A set of errors is correctable if and only if you could find some operator of B being the gauge subsystem such that this equation holds. And so let's now assume that this set of errors is contained in the n-qubit polygroup. We could ask, when is this set of errors correctable? So take any two errors in E. Well, in Pn, we want to know, we let E be this product because this product appears in this equation. We want to know when P times E times P is of this form. So if E is not in the centralizer of S, so if S being the stabilizer group, it means that E must anti-commute with some operator in the stabilizer group. So ES is equal to negative SE for some S. Right? And so now we use this equation, which says that if you so this says that if you do the projection of the code space and then you apply a stabilizer, it is the same as the projection. Or if you apply the stabilizer and then you do the projection, it is just the same as doing the projection. You could think about why it is not too hard. I mean, there are several ways to prove it. I'll leave it as an exercise. We could discuss this at the end if you want. But using this equation, we see that P times E times P is equal to P times E times SP, because P is equal to SP. And now we move S to the left of E. So we introduce a minus sign because ES anti-commutes with E and S anti-commute. And then now PS is equal to P. So now we get this is equal to minus PEP. So PEP is the same as minus PEP, which means that PEP has to be the zero operator. And in this case, we could just take GJK to be zero. Now, what if E is in the centralizer of S instead? It means that E commutes with everything in the stabilizer group, which means it preserves this subspace A tensor B. In other words, it sends anything in A tensor B to itself. Well, it sends anything in A tensor B to something else, possibly something else in A tensor B. And so what this means is that PEP will be equal to E on A tensor B. Because once you project onto the subspace, E would send something in the subspace to itself, and so this final P does nothing. And we know that this E is going to be off the form because E is in this centralizer of S, and so we know that it is going to be of this form. So if and only if E is in the gauge group, that's basically by the definition of what the gauge group is. And so in order for PEP to be of this form, it must be in the gauge group, which means that if it is in the centralizer of S, but not in the gauge group, it cannot possibly be written in this form. And so this gives us our conclusion, which is that a set of errors is correctable if and only if the product of any pairs of errors in our set is not a member of C, the centralizer of the stabilizer group minus the gauge group. Any questions? Great. I hope this proof is easy to follow. And so now let's go back to the rectangular Bacon-Shor code, which we discussed at the end of the previous talk. So we have an L by M lattice, and we have LM qubits on this L by M lattice, and the gauge generators are horizontal checks and vertical, horizontal X checks and vertical Z checks. Well, in the previous tutorial, I believe I swapped the roles of X and Z, but in order to align more with what's in the literature, I'm just gonna switch it back. Well, I'm just gonna use this horizontal X checks and vertical Z checks, but I mean, they are basically the same. So this is a picture when L is 6 and M is 7. So we have height 6 and width 7. Let me label these things by 0, 0, just like in a Cartesian grid. So 0, 0 being the bottom left corner up to 6, 0, and then 0, 5. So the subscripts here, so ij would just mean the ijth entry of this grid. So the gauge generators are basically, so say this, any horizontal line would be a gauge generator, and any vertical line, vertical segment of length 1 would be a Z gauge generator. And so we could ask what the stabilizers are. So the stabilizers are basically anything in the center of the gauge group, well, minus things which have the complex I in it. So the stabilizer generators, we have, turns out that we have m-1 x stabilizers and l-1 z stabilizers. So to visualize this, the x stabilizers are basically the ones that look like this. So you have two adjacent rows, two adjacent columns, and then you have all the x checks across the entire column. So these are basically all the x generated stabilizers. So we have m-2 of these. We have m-1 of these, and then the z stabilizers would be the ones that span across two adjacent rows. So these are the z stabilizers. And then we could ask what the logical operators are. And it turns out that there's exactly one pair of logical operators. It is given by basically a column of x checks, a column of x's, and a row of z's. So these, we could see they're anti-commuting because, I mean, they kind of overlap on one qubit with anti-commuting operators. So these are the logical operators. So you could replace this row of x's, this column of x's, with any column as well, because you could multiply the logical operators by any stabilizers, for example. So you could move this, you could multiply by the stabilizers which span the first two columns, and so move this x column to this second column and to the third column and so on. And same for the z's. And it turns out that the distance of this rectangular L by M Bacon-Shor code is the minimum of L and M. So, I mean, there are L many X checks here, and there are L many X operators here in this logical operator, and Z many, M many Z operators on this in this row. And it turns out that there's no way for us to multiply by any gauge generators to make like a smaller a logical operator of a smaller weight. For the rectangle, we are considering open boundaries. So it is like a little lattice. So I mean, there's nothing is big. I mean, there are no like identifications on the edges. So this is the Bacon-Shor code. Any questions? So there are L-1 plus M-1 stabilizer generators. And then there's one logical qubit, which means that there are well, you take Lm, which is total number of qubits, minus the number of stabilizer generators, minus the number of logical qubits, and this gives us the number of gauge qubits. So it turns out to be L-1 times M-1, which happens to be the same as the number of plaquettes on this. So a plaquette is just a little square, unit square thing here. So it turns out that there are L-1 times M-1 plaquettes in this grid. And this is, so it means that we could, for each plaquette, square plaquette over here, we could identify it with a gauge qubit. And so a natural way to do this would be to identify it with these. So we talked about virtual gauge qubits in the previous tutorial. So we could identify each gauge qubit with the virtual X operator corresponding to this qubit could be the product of all the X checks above it, and then the Z operator on this gauge qubit could be the product of all the gauge operators to the right of this. So you see that this X operator and this Z operator would anti-commute because they overlap in this one spot over here. And you would see that for any other gauge qubit, the X operator of that gauge qubit defined in a similar way, so anything above that, would commute with this Z operator, and the Z operator of that gauge qubit will also commute with this. So this and this would form if you define the X operator corresponding to this gauge qubit in this way, and the Z operator corresponding to this gauge qubit in this way, you see that you actually get like a set of virtual gauge operators in the same way as we discussed in the previous tutorial. Any questions? Right, let's move on. So in summary, we have Lm qubits on an L by M lattice. We have L-1 times M-1 gauge qubits. There is one logical qubit, and the distance is the minimum of L and M. And so these are the parameters of the big L by M big and Shor code. So that's N, K, G, and D. And so moving on, we have more examples of other kinds of subsystem codes. So we have a subsystem toric code. So a subsystem toric code is an L by L lattice, but this time with periodic boundary conditions. So what this means is that the edge on the left would be the same as the edge on the right. So this means, in some sense, this edge over here is the same as this edge. So you should think of kind of gluing together the left side and the right side together, and also gluing together the top and the bottom sides together. So if you take like a piece of paper and then you glue the left side with the right side, and then you glue the bottom end with the top end, you see that you get a torus, which is why this is called the toric code. So we have an L by L lattice. So in this case, L is actually 3 because we have 1, 2, 3. Recall that this thing is exactly the same as here. So this bottom row actually glues to the top row, and this. So in this case, L is 3, and we see that there are L squared vertices, 2 L squared edges, and L squared plaquettes. So plaquettes are just these little squares over here. And then we have 1 qubit at every vertex. So for every vertex of this lattice, we have 1 qubit, and for the center of every edge, we also put 1 qubit. And so we could compute that there are actually 3 L squared qubits in total for this toric code of L by L, from an L by L lattice. So in this case, L is 3, so there's 3 times 3 squared equals 27 physical qubits. And the stabilizers, so the gauge operators are these triangle operators. So we have these little triangles. So these are the X checks and these are the Z checks on the subsystem, on this lattice. And it turns out, well, so these things don't commute with each other. For example, this X check over here does not commute with this Z check, right? Because they overlap on 1 qubit. But it turns out that the stabilizers are, these form a kind of a set of stabilizers that generate the stabilizer group. So for each plaquette, you look at the 2 triangle X operators and the 2 triangle Z operators. So each of these would commute with every other triangle operator. It's not too hard to check. You look at this stabilizer and then you check the Z operators of every kind, you'll see that this would overlap each Z operator in either 0 or 2 spots. And same for the Z. That would overlap all the Z operators in either 0 or 2 spots. And so how many independent stabilizers are there? There are L squared plaquettes, so you would expect 2 L squared independent stabilizers, but these plaquettes are not all independent because if you multiply all, so just looking at the X stabilizers, if you multiply all the X stabilizers together, you see that every qubit is kind of counted twice. So the product of all the X stabilizers will be equal to the identity so that they are not independent. The last one is basically the product of the other ones. So for example, this plaquette is the product of all other plaquettes. And same for the Z's. So there are only L squared minus 1 independent X stabilizers and L squared minus 1 independent Z stabilizers, which means that there are 2 times L squared minus 1 independent stabilizers in total. And the number of gauge qubits is L squared. This can be computed in the interest of time. Maybe I would not do that here, but effectively we have, we have we have like kind of L squared plaquettes. So in each plaquette you pick one X and one Z to be kind of a pair of gauge qubits. And so the number of logical operators would be 3L squared minus the number of stabilizers minus the number of gauge qubits, and that's 2 logical qubits. And where are the logical qubits? They turn out to be, you could define the logical qubits as a basically a row of X operators and a column of Z operators across all the qubits in a row and column. And then you could switch the order around and define the other logical operator in the same way. So X1 would be just taking X across all the 2L qubits along this. So anything at the vertex and anything at the center of an edge, you would pick, and then same for the thing on the vertical. So these form a pair of logical operators. And so these are actually bare logical operators because they would commute with both the gauge operators and both the gauge operators and the stabilizers. But they are of weight 2L. Each of these are of weight 2L. And the distance of this code is actually just L. Because remember, the distance is the minimum weight of a non-trivial dressed logical operator. So we are allowed to multiply each of these things by one or more gauge operators. So you could, as an exercise, you could try to see if you could multiply, say, the X checks along this thing with appropriate gauge operators to get just a distance, to get like a weight L dress logical operator. Any questions? I mean, as a spoiler, you could just go to the reference. I mean, there's a proof in there. So now we could talk about the subsystem surface codes. These are basically almost the same as a subsystem toric code, except now we have open boundary conditions. So now the boundaries are not glued together. So the left boundary is not the same as the right boundary, and the top boundary is not the same as the bottom boundary. And this necessitates us to include additional checks, X checks on the left and right boundaries, and Z checks on the top and bottom boundaries. And in this case, we have, I mean, I'm just using L again in the same way as the toric code. So L would just represent 1, 2, 3. And so this is going to be L plus 1 squared vertices. 2L times L plus 1 edges. Well, you could count that. and then there are L squared packets. And again, we have one qubit at every vertex and one qubit at every set. Yes.
Sorry, Derek. So like basically, at like near boundary, you are measuring also that these triangle operators. But then other than that, you are also measuring these weight 2 operators, like X and Z.
Yes.
So basically on those qubits, basically, so there are qubits on which, for example, I mean the qubit where your mouse cursor was there at the moment, like I mean, so yeah, for example, there, like so you have like three operators are acting there, like one triangle and the other triangle and this X operator.
Yes. Yeah, so in this case, there are going to be, well, again, one qubit at every vertex and at the center of each edge. So these are the total number of physical qubits. You could just add the number of vertices with the number of edges. That's the number of physical qubits. And the stabilizers are the same as previously, but now also these boundary operators are also stabilizers. So they are gauge operators, but they're also stabilizers. You could check that they commute with all the other gauge operators. And the number of independent stabilizers, well, there are L squared many of these x's, L squared many of these z's, 2L many of these x's, and 2L many of these z's, because I mean there's L here, L here, L here, L here, of these 2 qubit operators. So in total, there are 2L squared plus 4L independent stabilizers, and the number of gauge qubits is L squared. Like previously, and so we could compute that the total number of logical qubits is just 1. And what is the logical qubit? The logical qubit turns out to be the product of all the x's along the horizontal row and the product of all the z's across a vertical column. This time we could not change this gamma to like a lambda and vice versa, because you would see that it would not commute with the boundary operators. If we swap the row of gamma and lambda, it would not commute with the boundary operators. And again, the distance is L by the same reasoning as before. Any questions? All right, so now we move on to the question of why we are interested in subsystem codes. So
I mean, like I have a very like naive, I mean, naive or maybe, maybe I mean, like kind of so let's say, so like some of these codes, right, the quantum codes like CSS codes and so on, using these products, like the product of chain complexes, we can understand them. But like have people tried, let's say, for subsystem codes, like you start with classical codes, or I mean, or if you think, like maybe it's outside the discussion, maybe we can chat later also. But so starting from classical code, and then you somehow incorporate the gauge degree of freedom, but you take appropriate product like on the chain complexes, and then try to define the like the subsystems. Yeah,
I don't know about chain complexes.
I don't know, because now it breaks, right? The regular the boundary thing breaks here. So
right. Yeah, I don't know about this. Yeah, I mean, people have tried constructing subsystem codes from regular classical codes, but not from. I mean, I don't know if people have done it with chain complexes.
Like still there is some structure at the level of stabilizers, but then like we have these grid, and I'm trying to think like whether still we can think of some homology structure, like where from where we can get like where the logicals live and so on, and I don't know, like I mean some modified version of a regular homological understanding.
I mean, that's a good question. I mean, I don't know. I think we'll need to think a bit more about this.
Hello?
Yeah, hello.
Yeah, I'm not sure if this is what Kishore is asking, but there is a paper by Dave Bacon about making subsystem codes using classical linear codes.
Yeah. I mean, so basically, Derek also said that there are these there. I mean, there is some research like where people start from classical codes and they try to construct it, but then sometimes like you use a product of chain complexes. So you model classical code as chain complex, and then you take their product, and appropriate product gives you the quantum code, and that people try for like many of the CSS codes, such as let's say hypergraph product code and so on. Now like I mean, basically, I was thinking that if one can do these things for subsystem codes directly at the level of like chain complexes, but maybe I think maybe it's a research question, or maybe like I mean, I think we need to think more. I
Um,
think that's what.
yeah,
Yeah.
I'm not sure if he's using chain complexes or not, but there is a paper by Dave Bacon on subsystem codes using two linear codes, and not sure how he has created that. I still have to read that.
Nice. Yeah, thanks.
Right.
Yeah.
Thanks. Yeah, so let me continue with why we were interested in subsystem codes. So last week we talked about check operators having reduced weights in subsystem codes. So instead of with 6x stabilizers, we have with 2 checks, x checks and z checks for the Bacon-Shor code. And the other important advantage of subsystem codes would be that they allow for gauge fixing. So we could measure a subset of the gauge operators which commute, and those would become part of the stabilizer group. So for each gauge qubit, we choose one of the 2 gauge operators, and then we measure those, and then we measure a bunch of commuting ones, and that would allow us to kind of fix some of the gauges and get like a bigger stabilizer group. So one advantage of this would be we get a greater flexibility in handling noise models which are biased. So for example, we have, so this is the Bacon-Shor code. So the typical way we do Bacon-Shor code measurements would be we measure all the x checks and then we measure all the z checks. And with this, we could compute what the stabilizers are. And then we could figure out if there are any errors. In fact, after measuring the x checks, what happens is that we have a bigger stabilizer group. So it's on top of the L-1 z stabilizers, we also have these L times m-1 x checks. So there are L times m-1 of these red x checks. And these would form the stabilizer group at this stage. So I mean, what happens is that we will measure the reds and then the blues and the reds and the blues and the reds. But after measuring the reds, we would get a stabilizer group, which is stabilized by all these checks, followed by, and also the L-1 z stabilizers. So it would still have one logical qubit, but this is kind of like the stabilizer group at this particular point of time. And once we measure the z checks, we would get a different stabilizer group. Now the stabilizer group would be the ones generated by the z checks over here, followed by the x stabilizers, the m-1 x stabilizers, which are basically kind of like the product across 2 adjacent rows. So there are m-1 of these products, m adjacent columns, sorry. And so if our system has more x errors than z errors, or has more z errors than x errors, then we could perform more x checks to try to kind of correct the z errors, and vice versa. We could, if the x errors occur more often, then we could do more z checks and then kind of correct more errors in that way. Any questions? So that's one advantage of a subsystem code. A second advantage would be that we get dynamical logical qubits. So what are dynamical logical qubits? So instead of doing the naive measurement like we did just now, we could have a special kind of measurement schedule. So this previously we had a period 2 measurement schedule. Here we have period 4 measurement schedule, where, so for example, in the first round, we would measure all the X checks except the ones along a kind of a column. So we would leave out all but one of the checks along a column in the first round. And then for the Z checks, we would leave out we leave out all but one of the rows, one of the checks in a single row. And then we do this like alternately in a period 4 manner. And so what does this give us? So eventually, so if we look at all the checks across all the rounds, we would still end up checking the same checks as we did in the previous measurement schedule, except in this case, at the end of each round, we are actually only fixing L-1 times M-1 minus 1 gauge degrees of freedom. So at the end of each round, we would actually get 2 logical qubits. So we have the standard logical qubit, which is a row of Z checks and a row of Z operators and a column of X operators. But we also have a second logical qubit, but this second logical qubit would differ every round. So for example, in this first round, a second logical qubit would be something like it would be a pair of X operators here and a pair of Z operators here, like on this row and this row. You could find more in this reference, or you could attend the next tutorial and the one after that, where we will talk about dynamical codes. So this is an additional advantage of subsystem codes, which is that when we could adjust the measurement schedule to get extra logical qubits. So in this case, we get 2 logical qubits instead of 1. And we also sometimes get more information to do the decoding step. So for the toric code, we have, let's look at the toric code. What happens when a Z error occur? So for example, if a Z error occur, it would affect the X packets and the X triangle operators. If a Z error occur on the edge, so if a Z error occurs here, it would affect the X packet here, and it will affect the X packet over here. If a Z error occurs here, it would affect again the 2 adjacent X packets. If a Z error occurs on a vertex of the lattice instead, it would affect the X packets on the top right, so this packet and the packet on the bottom right, because the Z error would affect this little triangle operator and this little triangle operator, which in turn causes this stabilizer and this stabilizer to be affected. And yeah, and any Z error will affect 2 adjacent X triangle operators. So what does this mean in terms of decoding? Well, if we look at the matching graph where we assume none of the triangle operators are fixed. So if we look at just the stabilizer, so each of these 2x2 square is you can think of each 2x2 square as a stabilizer. And you see that each stabilizer, if an error occurs, it would occur across 2 adjacent stabilizers, which explain the horizontal and vertical edges, and or it could affect 2 diagonal stabilizers, which explains the kind of this line from this stabilizer to this stabilizer. So without thinking about the triangle operators, thinking only at the level of stabilizers, placket stabilizers, we see that trying to decode we will talk more about decoding later, but trying to decode this system would involve a matching graph, which is a triangular lattice. And this turns out to have a lower threshold than if we were to just, let's say, after we did the X checks, so we know that the little triangle operators are fixed. So if we know that the little triangle operators are fixed, then any error would induce an error across any of these edges, right? And now we get a hexagonal lattice over here, which turns out to have a higher threshold than the triangular lattice over here. So decoding becomes easier, well, more efficient in this hexagonal lattice case than in the triangular lattice case. And again, you can go to Higard and Brockman's reference to know more about this. And finally, we could do code switching with subsystem codes. So the kind of prototypical example of code switching would be from a 3D color code to a 2D color codes. So depending on which operators which we choose to kind of measure. So here we would measure a certain set. I mean, maybe I won't go into this, but here we measure a certain set of X operators and Z operators. And here we measure a certain other set of X operators and Z operators. And in this case, we get a 3D color code with which allows us to implement certain gates natively and then transversally. And in this case, we get to implement a different set of gates transversally. So a transversal implementation of a gate is kind of like a nice set of a nice implementation where you could do things fault tolerantly. And yeah, so in this case, by fixing different gauges, you get different codes with where you could implement logical gates. Different logical gates for different codes. So this allows us to switch between different codes and, well, possibly do fault-tolerant gate implementation. So again, there's a reference over here if you're interested. And so in summary, we talked about the Knill-Laflamme conditions, and then we gave some examples of subsystem codes, and then we talked about what some of the advantages of subsystem codes are. And that is it. And so here is a list of references. That's all. Any questions?
Yeah. By the way, I would like to mention that Derek did not mention, but he recently has shown that whenever we want to do code switching, basically the code has to be contextual, almost always. Yeah. For all practical cases.
Right.
So it's a necessary condition. So many of you who are interested in contextuality, you might find that there is a link between contextuality and quantum error correction via subsystem codes.
Feel free to look at our paper if you're interested.
Yeah, and basically, like there's one more thing. Everybody's saying that AI is so powerful and so on. And we have a conjecture in that paper. And we tried that, I mean, multiple times with AI models and so on. So if you can solve that, conjecture using AI, we will be very happy. But so far, AI has terribly failed to so maybe it's an open question for AI also.
Yeah, who knows? Okay, all right. Any questions about the talk?
Okay, yeah, I have one naive question for the code switching here. So I don't know the basic idea for the code switching. Is it like an isomorphism between the two codes, or like
No, these codes are not isomorphic. No. Yeah, so these codes share kind of the same 15 qubits, but we measure it differently. So for example, in this 3D code over here, we would choose to measure, say, so for each cell, I mean for each of these like colored cells, we would measure, say, the X. We would measure like so each cell is like 8 qubits. It's made of 8 qubits. So we would measure, say, the X the 8-qubit X operator on each cell. And there are 10 other Z operators that we measure. So for example, we have like the inner faces. So we have 7, 12, 13, 14. So this would be an inner face. There are 6 of this. We will measure all of these 4-qubit Z operators. And then we would choose, we would also measure the faces as well. We would choose a face. So for each, we would choose one of the red faces, one of the green faces, one of the blue faces, one of the yellow faces, and measure the Z operators as well. So we have, so this is a 15-qubit code, and then we would measure 14 different stabilizers. So that would give us a 1 logical qubit, 1513 code. And over here, we would do a similar thing, but we have a different set of operators. So here we have we would do a 4-qubit X check on each of these 3 faces, and 4-qubit Z checks on each of these 3 faces. So that would give us 6 stabilizers. And this bulk over here, we basically want to just fix the state of it. So we could just choose any 4 faces. So none of them opposite with each other. Well, choose a pair of opposite faces and a pair of non-opposite faces. So maybe choose this 7, 12, 13, 14 phase, and then 8, 9, 10, 11 phase, and then this 7, 8, 10, 14 phase, and this 8, 11, 13, 14 phase. So choose 4 of these phases and do the X and the Z checks on those phases. That would give us 8 more. So 8 plus 6 would be 14 stabilizers. So we have one code with 14 stabilizers, but another code with 14 stabilizers, but these stabilizers are not the same. So they kind of they give rise to codes which are not isomorphic. In fact, we don't want them to be isomorphic because we want them to have different properties. We want one of the codes to have the property that it admits transversal T gates, and the other one should admit transversal H gates.
I see. So
Yeah,
it's
so
good for
yeah.
for the fault tolerance, like in the end. I mean,
Yes.
is it the target or motivation to do this? Like,
Yes. Because
okay.
I mean, the H, T, and C naught together form a universal gate set. So
Yeah,
the idea is that if you want to do if you want to apply a H gate, you would switch to this code to do the H operation, and then if you want to apply a T gate, you would switch to this code to apply the T operation.
I see. It's clear. Okay, thank you.
Any other questions?
Hi Derek and hi
Hi.
Kishore. Just I started to learn about the quantum computing. So I have a just I want to know how people do that. Like if we have a square and how we decide age give the x gate or and our circle or anything. How you deciding about the x and z? Like if you have a square figure, then how we can decide uh, which is the qubit, like which, like generally what I understand, vertex is saying that this is a qubit, but how we can decide that we have this one is the x gate and other would be the z gate? Just general question. I don't know exactly know what are going on in the. Do you understand?
Yeah, I mean, I roughly understand the question. I mean, from a mathematical point of view, it doesn't really matter because they differ by a unitary operation, right? Because if you, I mean, the X gate is really just a Z gate in a different basis. So you could think of this as like, yeah, I mean, I don't know if my answer makes sense, but
so in the figure, how we are deciding this this age product, like each age give the x gate or these age is give the z gate, how we are deciding that one? Like what I understand, we have a quantum quantum parameter like nkd, and
Yes.
K is the like logical gate, and N is the after converting the uh, after adding the redundancy what we get. But according to logical gate, how they convert in the figure, like we have some lattice, and how people convert and the decide we have a step.